Okay, what I want to share with you here is a quick relationship that ends up being very, very important for kinetic theory. And because with kinetic theory, we make some assumptions about the way that particles in a gas behave, that they behave like large objects do with a mass and momentum and energy. We can study a gas as being made up of many individual particles. So the system that we're looking at is a volume V that has a length L and area A for the cross section. And there's a single particle of mass M that's moving at a velocity C. We'll talk later about how we transition this to being a real gas, where there might be billions and billions of particles in here. And they aren't all moving with velocity C, but there's a distribution where the speed C is typical for particles moving inside of the system. And so this particle we want to think of as like an average particle, a typical particle, and we want to see how it behaves inside of this container. We're already familiar with the volume of this system. We're also going to want to think about the pressure, the number of atoms in there, or alternatively, the number of moles, and we'll want to connect to temperature. So we're going to be looking at PV equals nRT, or alternatively, PV equals nKBT. So this relationship is going to be important in a little while. Okay, let's start with trying to sort out where pressure comes from in this situation. And the place where pressure is going to come from is that our particle is occasionally going to be colliding with a wall of the container. So here's our cross section, A, and here's our particle. It has some sort of momentum going into the collision, some sort of momentum coming out of the collision. And because we assume that there's a single elastic collision with the wall, there's going a single energy conserving collision. We know that the horizontal momentum going in, we might call this Px, and is going to be exactly opposite the horizontal momentum going out, minus Px. And so the change in momentum for the particle is going to be 2 times m times c. I'm sorry, 2 times m times Vx, the horizontal velocity, which is obviously related to c, but because this is moving at an angle, it's not exactly the same thing as c. Now, these collisions are going to take place frequently and with many different walls. But right now, I only want to be concerned with this wall of the chamber. And so a little while later, this particle will have, maybe it'll bounce off the top, then it'll come back down, it'll bounce off this wall. And let's just assume that sometime later it comes back and it's going to have a second collision. How long will it take for that to happen? Well, that's also going to be related to this x velocity, because it has to traverse the length of the box and then come back. And it's doing that with the velocity Vx. So the next collision will happen at delta t is equal to 2 times the length of the box over Vx. Essentially, the distance that has to be traveled is twice the length of the box, and the speed that it's doing it at is Vx. And again, this is going to work because we're not really paying attention to, we're ignoring at the moment what's happening on these other surfaces. Okay, so what does this do in terms of the force? So the force that is experienced by surface A is going to be related to the change in momentum of the particle. Essentially, the change in momentum of the particle is a result of the force that the wall is pushing on the particle. And Newton's third law says that an equal and opposite force will be exerted on the wall. So what is that force? Well, the force from one particle would be the change in momentum over the change in time, averaging out over many, many collisions. What we can say is that there is going to be a force of 2 mvx exerted every delta t, where this is our delta p, here's our delta t. And so we can say that we have a change in a force 2 mvx over 2 times L over Vx. And rearranging this, we get mvx squared over L. At this point, we should start to be thinking, this looks a lot like kinetic energy, a 1/2 mv squared. The only problem is this is the horizontal velocity, not the actual velocity of the particle. So let's think about that for a minute. What would a typical atom be doing? So a typical atom moves in 3 dimensions, moves in 3D, not just 1 dimension. And without any reason to prefer one direction over the other, we might make the assumption that the velocity is somehow evenly distributed, right? That velocity might have, say, equal parts x, y, and z velocity. Vx, Vy, and Vz are all equal, so that there's a Pythagorean relationship between those 4 values, that c squared, oops, let me move that down just a little bit. C squared is equal to Vx squared plus Vy squared plus Vz squared. Now, of course, that won't be true for every particle, but in a little bit, we're going to change this to looking at billions upon billions of particles. So I think that it's a safe assumption right now. A more careful analysis of this problem bears this out. So it ends up being a safe thing to say that the c squared is equal to 3 times Vx squared. Let me see if I can just fit that in here. C squared is equal to 3 times Vx squared, where we assume that Vx, Vy, and Vz are all going to be about the same. Okay, so what does this do? We're going to just add another page here, and we'll put those two things together, remembering that we have the force of one particle is equal to mvx squared over L. And we have that c squared is equal to 3 Vx squared. We have those two expressions already. Now let's take a look at what would be the pressure associated with many of those atoms. Specifically, let's call it capital N atoms. Okay, well here, we'll move over to an expression for the pressure. The pressure is the force per unit area. The force associated with many particles should probably just be N times the force associated with one particle. And so we can write that as N times m Vx squared over L times A. or making the substitution for Vx squared is C over 3. 1/3 N over AL times MC squared. I recognize one more piece in here, that A times L, the cross-sectional area times the length. This is just the volume. And so now I have an expression for the pressure. Pressure is equal to N over V times 1/3 MC squared. Now things are starting to look really, really similar to something I mentioned a moment ago, right? We're starting to see some of the variables in here for PV equals N kBT. As a quick aside, if you're not familiar with KB, KB is related to the gas constant, R. You just have to divide by Avogadro's number. So recognizing this, that PV could be equal to N kBT, we rearrange this equation. PV equals N times 1/3 MC squared. Substituting for PV, we have N kBT is equal to N times 1/3 MC squared. And then the last little recognition that we make is, oh, this looks very similar to 1/2 mv squared, a kinetic energy. A last little bit of rearrangement gives us 3/2 kBT equals 1/2 mc squared, which is the kinetic energy of one particle, a typical particle. So we sometimes put the averaging bar over that. And that's where that relationship comes from. Or at least it's one simple derivation of where that relationship comes from, showing us that there is a direct relationship between temperature of a gas and the kinetic energy of the particles inside of that gas.